Okay, so I've taken out the constant outside of the integral. And now what we can do is we can change the limits of integration. So I'm just going to ignore the constant for now because if it's a constant, e total is proportional to it. So then I can change the limits of integration from negative infinity to positive infinity by writing eky theta times f of y dy, where f of y is the function, is a function known as a top hat function, where it's 0 everywhere except for between minus d over 2 to plus d over 2, where it's equal to 1. And so you see, even if you're integrating from negative infinity, it doesn't matter because you're multiplying by basically 0 until you get to negative d over 2. And then same thing on this side of the integration. Alright, so let me just rewrite this. So we have arrived at the fact that E total is proportional to this expression where you're integrating the product of some function f of y, which describes the shape of the telescope mirror, multiplied by e to the negative I ky theta, where y is the axis going from negative d over 2 to plus d over 2. Okay, well, it turns out, for those of you who have learned about them, this is basically the expression of a Fourier transform, where E total is the Fourier transform of f of y. And this is basically the reason why we care about Fourier transforms when we're looking at the optics of a telescope. And when you're measuring the intensity of the light on your camera chip, it's important to remember that intensity, which I denote by I, is proportional to E squared, which means that it is proportional to the Fourier transform, where I'm writing Fourier transform as this curly f, of the function that describes the shape of the telescope. And Okay, so at this point, I'm going to give you several Fourier transforms, and you should just commit this to memory. The Fourier transform of two delta functions that are spaced d apart is a cosine, where the period of the cosine is equal to 1 over d. The Fourier transform of a top hat function, which we used to derive, which we ended up with in the last derivation, looks like a sinc function. And it looks like this, with a taller peak in the middle, and each 0 is separated by, so if this is 0, then this is 1 over d, where this is 0, this is negative d over 2, this is positive d over 2, and this is negative 1 over d. Okay. And then finally, the Fourier transform of a series of delta functions all spaced d apart is just a whole bunch more. It's just another series of delta functions, which are spaced one over d apart. Okay, so how do you use these? Well, so let's say you want to build an interferometer with two telescopes, with a primary mirror, each with a primary mirror of size d, and place W apart. So the function describing this geometry would look like two hat functions, with the middle of each hat function W apart, and each hat function being d across. Okay? So everywhere else is 0. Okay, so then I want to know what its angular resolution is, or the angle that an object, that a point source in the sky appears to take up on the CCD screen. So I'm going to call this my f of y. Okay. F of y is basically two delta functions spaced W apart, convolved with a hat function of length d. And when I say convolve, what I mean is basically I'm taking this top hat function and just dragging it across each of these delta functions, and every little shift I multiply by the delta function, which is how you end up with 0 everywhere except two hat functions, like that. So the Fourier transform of the two delta functions is, like I said before, a cosine curve. With period 1 over W. And then the Fourier transform of the top hat function is a sinc function. Where the first 0 occurs at 1 over d. And then in the Fourier transform of a convolution is actually just multiplying. So this means that E total of a point source, when you view it through two telescopes that are W apart with primary mirrors of diameter d, basically looks like, so I'm going to draw the envelope of my sinc function, and then to make drawing easier, I'm also going to draw the opposite of it. So I take what I basically do is I multiply each point in the cosine in the Fourier transform of the two delta functions by its corresponding point in the Fourier transform of the top hat function. And what I get is something that looks like this. And then if I want to know I total, then what happens is I just square it. And so I get a total intensity that looks like this, where again the black curve is just for reference and the intensity field is this red curve. And the zero, the first zero of the intensity field, is at a distance 1 over 2W. Sorry, the period of the cosine curve is 1 over 2W because no, I'm being wrong. It's just 1 over W. Yep, which means that the first zero is at 1 over W, which is a lot smaller than 1 over D, the primary mirror size. So this means that the first zero, which is what defines your angular resolution, is basically defined by the separation of the two telescopes. So the further apart you place your telescopes, then the more finely placed together these maxima are, and the finer your angular resolution is. Okay, so in class you'll be working more examples similar to what I just showed you, but I think one of the problems will be for a spectrograph. For more resources, a good book is Chapter 2 of the observation and analysis of stellar photospheres. This is basically a discussion of Fourier transforms. It's written by David Gray, and he has a really good series of Fourier transform diagrams on page 34, and it's actually available on Google Books, so if you just Google it, you'll find it. And then if you have any other questions, then again, you can talk to me, or you can talk to Trevor or John or Professor Johnson in class, or at the talk sessions.